So now we start really 9 o'clock, the proper time, the conference. And it's my duty to chair this session that is very, very short and simple work to do, because and an honor for me, because I have the chance to announce this paper and this guy. He belongs to the barbarian that it was described before. So it seems that even barbarians can provide some good contribution to the culture and the science. I don't want to take longer, just allow people to come in, because I would like the room is full for this presentation. You know, everybody of you know Peter Morshuis. He's from DEIS University. And this is an award that is very prestigious, so I'm very proud to introduce Peter Morshuis for this award. That means that he did a significant contribution to science in our field, and also that he reached the right age to get an award. So it's not anymore so young. You see, all the people before were very old when they got the award. So it's time of Peter. Just to make short, really I'm proud for introducing Peter Morshuis. I don't think that there are too many people here that would merit more than him or deserve more than him this award. And it's time that Peter is trying to show us what he can do and what he can say. Thank you very much.
Thank you, Giancarlo Montanari. I will start using the microphone, but while we're preparing. Okay, now it's clearer yet? I think so. I can hear myself. The pointer. Okay, everything works. Thank you, Giancarlo Montanari. I think you are just too kind. And even though I come from a barbarian country, we were already there on the map. Maybe some of you saw, I saw it because it was my city, Lugdunum. It was Lugdunum Batavorum, it's Leiden. It's the city where I live. It's not the city where my university is. So we've been there for quite some time. So we put our mark on society here in Europe, I'm afraid. So, well, I am very, very honored to be standing here. I must really say so, and it's a great pleasure because this is the city, Bologna, I've learned to love since I first came here in the 90s and stayed for some time in Giancarlo's lab. And from that moment on, I was really captured with everything here, with the people, the colors, the science, and the food, of course, and everything. But I'm not going to talk about food today. This morning, I want to take you on a short journey. I hope it will not be too long. About interfaces. Interfaces is a topic that grasped me quite some years ago. And when I was asked by Andrea Cavallini to have the honor of being here for the Eric Forster Memorial Lecture, I thought, I'm going to talk about interfaces, about the kind of love-hate relationship we have with interfaces. So let me take you on this journey. These here are the ingredients of my talk today. Very roughly, I need to pay tribute to Eric Forster. So I will start with a short story about Eric, because I had the privilege of meeting him quite some time ago. Then I will introduce to you the interface, at least the interface as I see it. And maybe it's a bit more broad description than you would normally have for an interface. Then I will take you on the journey from very large, big things, big interfaces, to smaller and smaller and smaller and smaller interfaces, and try to describe to you how our appreciation of these interfaces changes when we go to very small size. And I will end with the listing of some of the things we think we know. So not things we don't know or things we know, but some of the things we think we know. But first, Eric. You know, the amazing thing was that it was very hard to find a picture of Eric. Maybe you noticed that this is exactly the same picture that Andrea has shown. And for me, it was really remarkable that a person who put such an important mark on our society, you cannot find a picture of the guy. Yeah? Anyway, we have the picture here. And for those of you, the younger people here who never met Eric, Eric was really the man on liquid dielectrics. He made a lot of progress in that field. And he worked almost his entire life in industry. But also he was involved in universities. And for me, talking about interfaces, he was kind of the perfect interface between university and industry. Very important, I think, especially in these days now. And, okay, please allow me to mention this. He was a good cook. He never cooked for me. Being in Bologna, I think I can manage to mention this. When did I meet Eric? I think it was about 25 years ago in the evening of one of the conferences. It was an evening with Eric. So that sounded interesting, so I went there. I was still young at the time. And Eric took us on a journey through the land of liquid dielectrics. And I was really grasped, was looking at an exciting movie. And because he was a gifted teacher, the man, I think. Always encouraging young researchers. I still remember when we met, said, oh, Peter, we need to talk about this, we need to talk about that, and so on. And he was telling us that evening about the importance of the interface between metals, between the electrode and the liquid. You see some very old pictures made of the start of a breakdown process in cyclohexane. It's a liquid insulating material with a needle as a cathode. Now, after that lecture, I was very much excited by the matter, and I spoke with some of the more experienced guys, and they were not so excited. I said, we didn't hear anything new, but I thought, I don't care, because it's the way Eric was the interface between the things in his mind and his audience that really grasped me. He was really able to motivate people. So, thank you, Eric, for that. Now, this lecture, what is it about? As I said, our love-hate relationship with interfaces. I'm going to try to shed some confusion around interfaces, so I hope you won't mind. Then my doubts about what we think we know. I think it's good to have doubts about things, especially if everybody is repeating other people saying the same thing. But do we really know? In 2007, John Fothergill, one of my predecessors, had a list of 10 things we do not know about dielectrics. So I'm not going to copy John. John is, for me, another league. But I want to tell you about 4 things we think we know about interfaces today. Okay. Let's have a look at some definitions of interfaces. Don't worry, I will start very broad with a long introduction, but then I will zoom in to the matter. There are different interface definitions. I think it's important to mention them. So it's the means by which interaction or communication is achieved at an interface. That's really what I'm doing here. I have all kinds of thoughts in my mind and trying to convey them to my audience here. And this is a very important interface indeed. Lecturers need to be able to do that. Then it's the place at which independent and often unrelated systems meet and act on or communicate with each other. My interpretation of this is that we have different fields of science. Where different fields of science meet, the most beautiful things can grow. So I think this is also a very important interface. And then, of course, this is the interface now that we're dealing with at this conference. So it's like a surface forming a common boundary between 2 bodies, spaces, or phases. Now, first, I want to say some positive things about interfaces, because it's easy enough to say negative things about them. So why is it the place to be? I think new ideas are born at an interface between different fields of science. I will give you a few examples, and you can find these examples at exactly this conference. For instance, we have the fields of terahertz and art. So we have a special session on this field. And it's amazing how you can use our dielectric techniques for exploring pieces of art. We have nanotechnology and dielectrics, very obviously. Yeah? We use the things that people in nanotechnology have figured out to improve our materials and components. Smart materials and power generation. You will hear one of our guys from Delft talking about elastomeric foils and that are being moved like this by the waves in the sea, and then electrical energy is generated. That's quite smart, I think. Yeah. Also this conference. Acoustics, HVDC, think of the PEA method. Electric fields, food treatment. So there are many, many fields where the interface delivers really nice information. Now why is it to be avoided at all cost? Professor Kreuger, maybe some of you still know him, he was my teacher, and at the time he said, interfaces are the weakest spots in our construction. So you should be very careful in your design with interfaces. Then the properties of an interface. What are the properties of an interface? They are very ill defined. And this is one of the problems here. They're heterogeneous. At the contact we can have local charging, which really destroys the design field we had in mind in the first place. Then heat cycling. In real life we have to deal with heat cycling. Can lead to delaminations, can create interfaces, defect interfaces. I try to make not too much noise here.
Yes.
So
it's noisy.
yeah.
Let's try another way.
It's nice to have a chairman taking care of you.
Oh yes, like a wife.
Don't overdo it. You make me nervous now. I don't want to be nervous while standing here in front of all of you. So okay. Now it's better. Okay, it's better. Okay, so okay. Let's move on because time is running. Now, another reason why interfaces, and you might not think of that in the first place, is why they're a problem in real life, because any interface impedes the transport of heat. And in our components, of course, heat is generated due to losses, and we have to get rid of it. And our high voltage components are becoming bigger and bigger and bigger. Higher voltage classes, our components are becoming thicker and thicker, so it becomes more and more difficult to get out the heat from solid dielectrics. They're pretty good thermal insulators. So let's introduce you to the journey. I made a division into three categories. Large-scale interfaces, which is really the size of centimeters to meters. And these are the bulky products we see in practice, such as high-voltage cable accessories. There's one here. It's not so clear, but here you have the cable insulation. Here we have the body of a joint insulating system. This is the place where often we have the problems, if any, in a high voltage cable system. It's at the interface. And these interfaces can be quite long, can be meters of length in HVDC systems. Another example that often poses problems is the interface in GIS insulation, spacer insulators. Yeah? It's not so easy to design spacer insulators for especially HVDC applications. Zooming in a little bit, we have the medium scale interfaces. I say it's micrometers till millimeters. And you can give many examples of this size of interfaces. I decided to focus on defects that we have to deal with in real life, and they pose these medium scale interfaces to us. So I'm going to talk about that later. So you can think of cavities inside insulation, protrusions on the electrodes that may lead to these nice trees. Small scale interfaces, of course, nanometer scale and so on. Started in 1994 already. It's roughly 20 years ago when John Lewis spoke about nanodielectrics and the possibilities there. Now we have so many papers at conferences. It's amazing. At the time we thought it might be a panacea or a healing for all our dielectric problems. By now we know it isn't. You see some pictures here. Let's start here. This is a needle. We think that the right treatment of a medium, putting in the right treated nanoparticles, can hinder tree formation and increase lifetime. This here is more like an artist impression of one of my former PhDs who is here, which is an artist impression of how heat is transported through interfacial zones in nanocomposite. Okay. The nature of interfaces. You need to talk about that, because broadly speaking we have mechanical interfaces. You just put two systems together, like in a pre-molded joint in a cable system. You put two systems together, maybe you interpose a little bit of liquid as a third medium to get rid of voids and so on, just to match the two materials. Then we have chemical interfaces, where we have chemical bonding between two systems. It's a totally different kind of interface there. And looking on nanoscale, you could consider nanoparticles that have been surface treated to be chemically bonded with the host material. Now talking about interfaces, well, we know it's not two-dimensional, it cannot be. So it is a three-dimensional concept. And especially if you look at it on a microscopic scale. So we better talk about an interfacial zone, or as somebody from Germany said, an interface with pH. Here. Now if you zoom in onto an interface, this is an interface between XLPE and the semicon layer. You see already that it's not such a sharp distinction between the two materials. And if you scan from left to right through the system with Raman, you see that the properties only gradually change. So you have an interfacial zone of a number of micrometers in which you go from one medium to the other. And in between, you have something that can be, let's say, the average of both materials, but it can also be something which has completely different properties from the other two media. And this is interesting. Okay, our journey, large-scale interfaces. I want to give you an example of a large-scale interface of which we think we know how to explain things, but where I have still some doubts. And as an example, I take an interface in DC, cable insulation. It's a very challenging topic. And we know that under DC stress, interfaces under DC, they play a major role in determining how the electric field is being distributed and how it changes as a function of temperature distribution in the system and so on. Well, the question is that I want to pose: how well can we model the charge dynamics at this interface? I know Len de Sado yesterday spoke about that. I think from that his story it was clear that we haven't really reached the answer to everything there. Now I want to start very simple. Forgive me for that, because I like first to look at things by very simple models. So if we have a system consisting of two media, there's this classic theory by Maxwell, Wagner and Sillers, which shows you how you can calculate the charging of the interface if you have access to the macroscopic parameters, conductivity and permittivity. Very basic, very straightforward, but very easy to check. And then you get this exponential growth of the surface charge at the interface between two dielectrics. Now we know that conductivity is not a constant parameter. It is very strongly affected by temperature and by electric field, in fact. So we have to use an equation which, for the conductivity, which accounts here for temperature and for the electric field. So you do that. What are the results? Now I go too fast, sorry. For this temperature dependency, you have to do measurements. You can measure, for instance, the conduction current as a function of applied field. And you plot that in an Arrhenius graph. And usually then you get these nice lines here. Here you see the Arrhenius plot for two different materials, EPR, the one here, and XLPE. These are two typical materials for HVDC cable systems. For the field dependency, here it becomes a little bit more complicated. Here you see a plot of the conductivity as a function of applied field. So up to a certain value here, you see we have almost constant conductivity, ohmic behavior, easy modeling. But above a certain threshold field, the threshold for space charge accumulation, we see a deviation from ohmic behavior. And we have to deal with it in our model. Now, then we have the interfacial region. So if we have a mechanical interface, we have to model in some way the properties of the medium we don't know, the uncertainties. So you could introduce a third layer, for instance, a silicon oil layer which matches the two media. And you can use a 3-layer Maxwell capacitor. Okay, let's have a look at the results. Here are the results of simulations and experiments on a system, a cable where we had two dielectrics, one EPR and one XLPE layer. It's a kind of, let's say, a model for HVDC cable joint. Okay, if you put on a polling field and you wait for some time, you have to look at the right column here. This is the space charge distribution, which grows in time, as you can see here. And if you look at the field, the electric field that corresponds, you see that the maximum of the field moves from the inner conductor to the outer conductor. Okay, that's the measurement result. What do we get when we model it with our simple model? We get something that looks quite similar. Yeah? So the question now is, can we be happy or satisfied with this as a modeling tool? I would say to a certain extent. Because what happens if we further increase the field? I already mentioned the threshold for space charge accumulation. Meaning that at some point in time, at a particular field, the insulation is no longer ohmic in behavior. Well, what do you do then? You get charge injection, extraction, trapping processes. Len told us all about that yesterday. Here you see the threshold where this happens, obtained from two different measurements. Conduction current measurements here, space charge measurements here. And you see for these materials, we have this threshold around 10, 12 kV per millimeter. It's important because in practice, we will always use fields above this value. So we have to deal with space charge trapping. To show you that you really have to do that, it's not just theory. I have this example where again we have the system consisting of EPR and XLPE, polling voltage of about 20 kilovolt, then increasing it by a factor 3. Our model predicts that the amount of charge at the interface would be tripled. Well, evidently it's not. It's even smaller than it was at the lower voltage. So we're missing something here. And what we're missing here, in fact, is injection, all the things that Len has been talking, I see him smiling, all the things that Len has been talking about yesterday. Injection, extraction, charge trapping. But how do you model that? You have to assume a number of things. And the people in Toulouse, they assume a kind of a third layer if you want to model the charge behavior at the interface between electrode and dielectrode. Close to the surface of the electrode, they assume a different distribution of trap depth and trap density than in the bulk of the material to be able to explain and to model the charge behavior. But then you would have to answer things like, how thick is this interfacial region? What is the trap distribution? So, okay, in comparing your results with modeling results with experiments, you have parameters that you can tune and so on. But really, how thick is this region? I would like to see it. I would like to see things. So it's not finished, this yet. Let us zoom in a little bit further now to medium scale interfaces. I told you I will focus on defects as small scale interfaces. And defects are very important, I think the main source of interfaces at this scale, if we like it or not. And an important family of defects consists of cavities, delaminations, or regions of low density, if you like. The question is now, do we really know the route to failure? This is a very old topic. People have been discussing discharges in cavities and how they reach breakdown for I don't know how many years. So I realize what I'm doing here. I'm shedding doubt on something that we all take for granted. But that's just the reason why I'm doing it. So, because this is how we think it works. I would say, correct me if I'm wrong, but we're not going to have a discussion now. I know it's not going to be like that. So what we do, we have a low density region in which electrons can be accelerated, give rise to ionization, bond breaking when they hit the interface, pit formation, field concentration locally, electrical treeing, and failure. Yeah, this is the story, isn't it? Yeah? And everyone is citing others, and they're citing others, and they're citing others. And if you follow that path, you will go around in circles, it seems. And you may ask yourself, did we prove all the different steps, the existence of all these steps in reality? I'm not so sure. I see somebody nodding no. So, roughly again, it's a bit of an illustration of what we think happens. Okay, we see that this is the gas, this is time, this is the dielectric. We see changes in surface morphology, for sure. I saw it many years ago. Like you get discharge byproduct and so on. You see crystal formation, field enhancement. You see partial discharges, focusing on these crystals, points of field enhancement. We even see pits. This is a picture that I made when I did my PhD. It's the same spot as you can see, but focused at two different heights. So this one is focused on the surface of the dielectric, where you see the crystals here. And this is focused just a little bit below, where you can see here there's a kind of crater going in. And then I wrote, of course, the next step would be treeing. I never saw it. I never saw it. But I assumed that would be the next step. Because we all know that it's not good to have cavities in the dielectric and they affect breakdown strength. So I just assumed, I cited people, also cited other people, and so on. So there's proof for all stages, except, I think, this very important stage. So this is what I had in mind. But then, a week ago, when I was preparing this lecture, I was rethinking things, rethinking should I really say these things? I went back in time in literature. I went back in time. I saw papers of you, Christian, mentioning, Christian Longa did a lot on treeing and so on, and he mentioned other people, went back in time. And then I, oh wait, I'm missing something. First this. Then I arrived in 1952, before I was born even. It's amazing. There was a man who was very famous in our field, John Mason. And there's a paper where he showed some photographs, which are maybe not so very clear. This is one. He made an experiment on a flat cavity, a cylindrical cavity that we all know, and he showed that from the edges of the cavity, things were growing after accelerated aging, after a considerable amount of time. And these things, what looks a bit like a tree, or it's a bit tree-ish. Huh? But okay, this is the edge of artificial cavity, the kind of cavity that we will normally not encounter in practice. Yeah? We would expect more spherical cavities. Okay, so But Dr. Mason was quite smart, so he expected that, I guess. So this is a picture of a dielectric with a semi-spherical cavity on one of the electrodes. And he showed that indeed there was something growing there on the bottom of this semi-spherical cavity. Well, is it a tree? It doesn't look like a tree, but certainly it's a degradation process going towards the other side. He was not even satisfied at this point, I think. So in the same paper, he showed this. This is a slice of material taken from a cable that broke down. Here there was the conductor. You can see the conductor screen here. A huge bubble. And definitely a tree on the bottom. So then I was confused because I already had prepared this lecture. What I'm going to do now. What to do with this information. I knew that all around the world groups are trying to create an electrical tree from a cavity, and I know that they haven't succeeded until now. So my question is, did we find the missing link by just tracing down this old paper by John Mason? Did he really see trees? I don't know. And why nobody was successful in repeating his experiments so far? And if we did find the missing link, why do trees start to grow at much lower fields than required for treeing from a needle? Just to explain that a little bit more in detail, let me go back a few slides, because I skipped one on purpose. This one here. We all know that from a needle, a certain potential, when the field is high enough, we create an electric field. Yeah? And the idea is that a conducting pit at the surface of a cavity also gives us field enhancement. So the precursor for electrical treeing. But let's make a very simple calculation again. I like simple things, as you know now. This is textbook stuff. If we have a protrusion here, the amount of field enhancement depends on the aspect ratio. The larger the aspect ratio, the larger the field. And roughly, this is the amount of field enhancement we have. The length of the protrusion, and this is the radius. Let us assume a needle with a length of 10 millimeter, 10 micron radius. We get 1,000 times field enhancement at the tip. So, easy enough. Now we take this starting cavity, which is about, which only has a radius of 10 micron. And we get field enhancement of 3, maybe 10. So normally we would be far away from the conditions we would have at the needle. So still, I'm in doubt here. What is the exact process? So go back. So I have my doubts here. I think there's work to be done. Now I'm going to zoom in even further to small scale interfaces. And we know now that everything is different, or seems to be different, at nanoscale. Also interfaces. And the interesting thing is that I've said these were negative things about interfaces that I showed you. The problems we have with charging at interfaces, understanding it, the problems with defects. But now all of a sudden our feeling towards interfaces changes. We think the most beautiful things are possible with interfaces, by tailoring them. And when it comes down to a proper understanding of these changes, we all generally attribute these changes to the interfacial zone, this concept. But what is it? My question is, maybe we burn our fingers on the nature of the interface, assuming so much without really knowing things. Okay, let me explain. There are a number of models that try to explain our experimental results. First there was John Lewis, then Professor Tanaka, who is here with the multi-core model. Then from Germany, Stefanie Retzke had the interface with pH model. And then one of the guys from my lab, Thomas Angrich, had this polymer chain alignment model. Let us have a quick and brief review of these models and see what they assume. Lewis's model It's basically, it's very simple. It tells you that the intensity of any property across an interface changes not abruptly. As you can see here, property I, alpha, which changes gradually when you go across the interface. And this can be more special. In fact, the intensity can even attain values which are larger or much smaller than both media, which is really exciting. So we create something which is really different from both constituents. The model, however, does not give any physical explanation. It's more like a visualization of what could happen on a nanoscale. If we go to Tanaka's multi-core model, Tanaka tried to focus more on the physics, what's happening really there on a nanoscale. He worked with different layers, where the first layer is really where the polymer is coupled to the nanoparticle. Maybe it's just one atom or molecule thick. Then the second layer is the layer where the polymer chains are reoriented in the vicinity of the nanoparticle. And that influences, of course, the chain mobility locally. It's like a kind of cross-linking and the orientation. And then there's a third layer further away where there's less interaction, but still there are morphological changes to be expected. Now, this model is an excellent basis to start to explain the phenomena that we observe in nanocomposites. But still, it's not the explanation of what we see, of course. Then there was Stephanie Retzke, who did some interesting things. She related or correlated the amount of interfacial volume now to the change of some of the properties. So the resistance towards partial discharge, treeing, that should be treeing, and arcing. And what she did, she assumed spherical particles with an interface thickness of 10 nanometers and a body-centered crystal lattice unit cell. And if you do that, and then she saw something interesting, that you see that you attain maximum values for the interface volume fraction depending on particle size. And you all know, I guess, that there seems to be some magic optimum for the fraction of nanoparticles to change a property. Let me show you. These are plots from Stephanie Retzke, where you see this here on the y-axis all the time is the interface volume, and it's plotted as a function of pillar content. This is weight %. And then for different size nanoparticles, 20, 30, and 40 nanometers. And you see, follow the red lines, that there's a peak in the amount, in the amount of interfacial volume. Meaning really that if you add more nanoparticles, that interfacial zones are going to overlap, and you don't get any more. And there are results, for instance, of relative permittivity, where we see that depending on the amount of nanoparticles, the fill grade, the permittivity goes down, but above a certain percentage it goes up again. Or breakdown, we have found an optimum for a certain fraction of nanoparticles, and Stephanie Retzke was quite smart in relating the total volume of interface to the change in these parameters. Now the last one was Thomas Andrich with his polymer chain alignment model. Thomas again, because Stephanie Retzke didn't really focus on physics, as you saw. Thomas again tried to focus on physics. His model aimed to describe the morphology in the vicinity of the nanoparticle, how that is affected. And he showed that surface functionalized nanoparticles, they lead to an alignment of polymer chains in the vicinity of the nanoparticle. You can see here that this particle has not been treated, and you see there's a very weak interaction between the polymer chains and the particle, while here, where the particles have been treated, the ends of the polymer chains, they end perpendicularly on the surface. So you see there's a rearrangement of chains here. And what he said was that due to this rearrangement, you could see this interfacial zone as a zone where we have a changing crystallinity, more order in the material. And he claimed that that would be the reason for many of the observed changes. One of these changes is this one here, of course. And let's see if we can explain this change with any of the models that we have seen. This is the relative permittivity across a broad range of frequencies. This one is a magnesium oxide epoxy resin nanocomposite. This is the base resin. Now you add high permittivity nanoparticles to this resin and the permittivity drops, which is kind of strange. Yeah? And people started to model this behavior by assuming that the third medium, the interfacial zone, has a strongly reduced permittivity. Yeah? So you have then a three-phase system which would result in these drastic reductions of permittivity, up to 20%, which is quite a lot. However, for correct modeling, assuming that this is the working principle, we would have to assume an interaction of the nanoparticle with the surrounding areas that extends way beyond what we think is possible. So here again we are at a loss. So that's why I posed a question, I think it was a few months ago on ResearchGate, maybe some of you know it. I said, does anybody know how we can visualize or see this interfacial zone? Because I want to see it, I want to see the restructuring, I want to see its extension, because it's important for understanding why we see the things we see. And what is the morphology, what is the thickness? So I got a number of answers there. There were some people said you should use PALS as a means for probing the free volume around the nanoparticle. So I dived a little bit into that kind of literature, but the results are quite contradictory there, so it doesn't really help. So if you start reading and then don't look at the contrasting opinions, yeah, then you have your explanation. But that's not the way science should be done, of course. So they are partially contradictory. So some people see the amount of free volume from which the thickness of the interface can be calculated, yeah, grow. Some of them increase. Some of them they see it as decreasing. So what to think about that? It is clear, however, that the way we made the nanoparticles compatible with the host material has a strong influence on whether we get an increase or decrease in free volume. In the end, most studies, but nobody has ever seen yet the interface, conclude that the thickness of the interface is around 10 nanometers. But again, it's by far not enough to explain what we see. So there's a lot of work to be done here. A totally different example here. We're still on the nanoscale, very small. Thermal conduction, as I mentioned, is becoming more and more important in our field. And in the micro world, the thermal conductivity increases when we add fillers of high thermal conductivity. Epoxy resin is always filled, 50–60% of silica, for instance, to make it cheaper, of course, to tailor the mechanical properties, the thermal properties, and so on. We can easily calculate the thermal conductivity of the composite by classic rules of mixture. No big science there. However, we know that the effectiveness of heat transport determines very much on the amount of scattering of phonons, let's say the heat carriers, at interfaces and at imperfections. So in the nano world, we would expect a huge number of interfaces to affect. Is that me? That's strange. What did I do? It was you. sorry for that. You need to perform better, I think. So we would expect a lot of scattering in nanocomposites, yeah, wouldn't we? So you would think it doesn't make any sense really to add nanoparticles to improve heat transfer from this perspective. But then we are surprised again, as so often we are. So I hope you can see this, otherwise I will tell you what it says. So these are some practical results that we obtained also in Delft. Here we have a nanocomposite. Polypropylene was the base material. I will put my pointer now to the left. Sorry, I don't have a stereo pointer yet, but would be nice. We have a volume percentage of 30. That's quite a lot. We have two different fillers. The one is copper conductor. So we think that would really boost the thermal conductivity. The other one is talcum powder. Huge difference in thermal conductivity, 400 of copper and about 10 for talcum powder. But then when we measure the resulting thermal conductivity, we see that the talcum powder composite wins. The resulting thermal conductivity is twice the one of the copper composite, which makes you wonder, maybe. Another graph is, this is the graph we would understand, yeah, because here we see this is a silica epoxy resin composite, fill grade, thermal conductivity. Blue is nano silica, red is micro silica. We see that the micro composite wins. That's what we would expect. More scattering in the nano composite, so less conductivity. However, here in this table here, we are focusing on epoxy resin boron nitride nanocomposite. And we have look at the first row and the last row. These are both spherical particles, but in the first row we have nanoparticles, in the last row microparticles. Same fill grade. We see that they have comparable thermal conductivities. This goes totally against, at least my expectations. So, in order to know a bit more about this, we need to look a little bit at phonon scattering. Okay, we know that interfaces, it's a bit strange animation here now, but interfaces provide added sites for phonon scattering. And we can define a thermal interface conductance as the applied heat flux divided by a temperature drop across the interface. And this is very important, that's why it's bold, of course. The thermal interface conductance is highly dependent upon a possible mismatch between the vibrational spectra of the two media. So different media have different phonon vibration spectra, and if they're unmatched, totally different, if they have no overlap, you have a really big resistance for your heat transport. Let's have a look. I borrowed something from rather recent literature here, and that is matching the density of states of phonons in the two materials composing the interface. So these people, they use molecular modeling of density of states for a range of vibrational frequencies. And first they show a mismatch between material A and B. Here we have, these are all molecules here, material A and material B. And they calculate the vibrational spectra for both of them. I will show them to you in a moment. And they show that by interposing an extra layer, which normally would be very ineffective for thermal conductivity, in this case it boosted the thermal conductivity. It's like, again, it's matching the two media on both sides of the interface. In a way, it's quite similar to some of the tricks we use in PEA measurements, where we have to match acoustical properties of different materials. It's quite similar. Because here, all the vibrational spectra, you see this is frequency in terahertz, by the way. This is density of states. This is the spectrum of material A, this is material B. You see that only here there's some overlap, where there's kind of optimal heat transport. Now by interposing a layer which overlaps with both materials. They have calculated that we can improve heat transfer by at least 50%. But this is very interesting. Again, we need to make different media compatible with each other. And the interesting thing is that we can use molecular modeling now here to really tailor the interface. Because they also looked at what is the effect of making a little bit more fuzzy interface, more diffuse interface. And then it appeared that a certain amount of diffusiveness further improves heat transport. I will not tread into details, but you can have a look at the paper if you like. Now, let's look at experimental results coming from people. Yeah, I need to run. Yeah, okay, good. So just a few experimental results. Boron nitride, treated materials, there was an increase of 3% after treatment of the surface. It's not so much. Polyamide nanocomposites, increase of 11% after treatment of the surface. Aluminum nitride composite, 13% higher thermal conductivity. So it really makes sense to do this treatment. So it appears there will be much further improvement possible. A lot of further improvement possible. Now, I will skip this exciting topic, the dangerous part, but we can touch, it's about liquids, it's very, but I want to say this. I put it in, this is not a liquids conference, but I think it will be very good if we would have some liquids people inside here to learn from them. Maybe they can learn a little bit from us, maybe they will not admit, but that could be the case. Anyway, that's the next couple of slides, but I will skip them because I'm going to be too over-enthusiastic. But later on, during coffee, I can speak about this. So finally, focusing in. The idea of this is that you see the different materials disappearing. Now if we zoom in, we only have interface zone. And this is exactly what's happening, of course, in the nano world. So our appreciation of interfaces, these are my conclusions, Mr. Chairman. So it's complicated. But what we do not know, we fear, in fact. So much more understanding of nano, of interfaces, makes us able to tailor them in a better way. We don't have to be afraid of them anymore. So whatever the application, a proper matching of the two media will bring optimal results, and molecular modeling will certainly help here, as you'll see. And we've seen that our appreciation changes, becomes more positive once we get more to nano, which is nice. So 4 things we think we know. Quickly, one about charge dynamics at interfaces. We are not there yet. This is not the way a lecturer should work, as it goes so fast. I realize that, but okay. So as yet we have to wait for a generic model that really explains and describes the experimental results on interfaces between dielectrics. That's really what's it about. So that's one thing we think we know, but I doubt. Then from cavity to electrical tree. Do I have to explain further? I think you remember, yeah, what was the message. The nature of the nanoscopic interface. Please show it to me, I would like to say. Thermal conductivity at nanoscale. Very interesting. And here we can make major steps in using other fields again. Molecular modeling, for instance. I'm sorry, this will stay a mystery for you, I'm afraid. Okay, I've come now to the end of this short or rather long journey, maybe. Well, I don't want to stop without having some fun. Of course, no, I really need to thank quite a number. I'm not going to thank everyone, but some people made life for me very exciting. And really nice, and really motivated me to go on in this field. And you can decide who is John, Paul, George, or Ringo. I don't care. So But apart from them, there are many more people, but of course my students, some of them are here. The ones that I have now are really great. Last but not least, my teacher, Professor Kreuger, who explained to me how to sell things. Well, I hope I sold you something today. Thank you very much. Yeah.
So, we have, first of all, I have to thank Peter for his very, very nice presentation. I think that there are many questions, but we have just 10 minutes of time, so please try to be very, very short your questions and get Peter your answer. Yes.
You don't have a microphone?
Yes, you can use this one, I guess.
Oh, no, I have, but he doesn't.
Thank you for this very nice presentation. You emphasize the interfaces, and what we observed is that what concerns breakdown, triple points are even more critical. So what do we know about them? Even less, I guess.
Yes, you beat me there. Of course, talk about interface, the triple point is really a yet more unknown and dangerous area. What do we know? What do we know about the mechanisms at triple points? I think we know quite a bit about what's happening there. Of course, at the triple point, we have the source of charge carriers, the electrode. Often we have some field enhancement at the triple point, so optimum conditions for charge injection. Then often we have a solid dielectric and a gas. Perfect conditions for charges to hop and to multiply. So I think especially people working in gaseous systems and vacuum, they can tell us a lot about these processes. And also about how to deal with them in practice, which might be even more important. I can say more about that, but it would take too long now, but maybe during the break.
Yeah, there are other questions. Can you introduce yourself before your question? Please, John.
Tanaka is my name. Thank you very much for a nice talk on the interface. Roughly speaking, the interface is impede of the electron scattering. And also the interface impede the phonon scattering. And as far as electron insulation is concerned, electron scattering is better. And maybe it allows you inhibition of the tree or as a partial discharge cell. But as thermal conductivity, take thermal conductivity, phonon scattering, it decreases the thermal conductivity. So it's avoided or it's treasured, maybe electron scattering to be treasured. But as far as the thermal conductivity, maybe it should be avoided. And we need some another idea to match to increase the phonon scattering. Decrease phonon scattering. Is it okay?
Of course, our goal is to improve both. Yeah? And if the result of that is that, okay, we match for phonon transport. If the result is that we have less electron scattering, you would not be happy with electrical trees. Yeah? Or the other way around. If we increase electrons scattering and in the same process increase phonon scattering, so it's a trade-off as usual in life. We should find an optimum there.
Can I go on? I'm Karl-Michael Weitzel from University of Marburg in Germany. You asked for a technique for visualizing interfaces with a pH, and you mentioned microscopic and electrical measurement, and we discussed scattering techniques. I would like to propose something different, to use depth profiling. We do depth profiling by means of TOF sims to quantitatively determine the composition of an interface over a thickness of as many nanometers, up to 100 nanometers. You can even combine that that with photoelectron spectroscopy, and that will give you the information which you need on your interface.
I'm very happy to hear this.
I can give you more details later.
Okay. Wow, that's great news, I think. So we'll be in touch about that.
Rongsheng Liu, ABB Corporate Research. You have mentioned about the thickness of the interface. Then if we go to other direction, say the area, traditional people talk about the area effect and so on. Do you have any comments on that?
Sorry, I didn't...
The area effect.
The
area.
The area?
Yeah. Volume.
The volume.
It's not volume, it's area along the interface.
To comment on the area, that is the surface area. Yeah. Well, at the surface area, everything is determined by bonding, proper or improper bonding of your host material. So whatever you do to the surface of your nanoparticle, it needs to rearrange the polymer in the vicinity of the nanoparticle, because otherwise nothing changes. Okay. So I don't know exactly where you want to go here, but again, whatever you do, that's the result in the change of properties of the interfacial volume.
Because if we see the product, if you increase the area of the product, if you increase the size of your products or designs and so on, you get the large area, so to speak.
Okay, we take larger particles, but for the same weight fraction, you will have much less large particles than small particles. And we know that for the same weight fraction, if you go down in size, you get more interfacial volume. It's as clear as that. If you want to use big particles, you can, but you need much more to create the same amount of surface area as that we create for nanoparticles. So it's not really an option, I would say.
Because this comes to an issue how to modify this situation. Maybe it's a three-dimensional issue.
Perhaps. Thank you.
Okay, so I think that it's 10 o'clock. I'm sorry to stop the discussion, but the paper took a long time. But I think that we have to thank again Peter Morshuis for his excellent presentation, and then we are waiting for some communication from the chairman. Thank you very much, Peter.
Thank you.